All right, let's finish up this problem here that we were working on. So what we've done here so far is we found the mass of the door. We went through that last time. And now let's find what I would call the dynamic reactions. So the dynamic reactions here on the door are going to be basically the XY reactions. Okay, let's not worry about the Z, which are primarily caused by the weight of the door and statics and things like that. So let's just focus on the dynamic reactions here. And what we're going to do, what I'd like you to do first here is to look down on the top of the door. Okay, so here's the door, and it's kind of a, obviously a three-dimensional object, so it's got a little bit of thickness there, like so. And let's start up here, and let's look down at the door and draw a free body diagram of it. So what you're going to end up with then will be a rectangle, okay? So why don't you draw a rectangle and put the forces and accelerations on that you think you'll have to deal with. Our goal here is to find the dynamic reactions at the hinges. All right, so why don't you do that on that little rectangular type shape. Now the door obviously is going to start horizontally, and then there will be a push exerted on the door. And I'm sorry this is getting a little messy in here. I've got a lot of stuff in here, I know, but I just want to illustrate something kind of simple. The door is going to open up to a 70-degree position. It's going to swing around like that. So let's just take the position of the door here, even though it's angled, and let's draw it flat like that, just so we got a nice simple sketch going. So why don't you draw that rectangular door in the position shown, and then see and put the forces and accelerations on that, and pause the recording and do that, and then come back and we'll have a look at it. Okay. All right, so here we are. So we're going to have the door there. Now what we're going to have here are two reactions. One that's going in the tangential direction, and what we're looking at here is the center of gravity. And we're going to have a tangential acceleration. And of course that's going to be r alpha. And then we're also going to have a normal acceleration. And these are both of the center of gravity, because that's the point that we kind of reference here. All right, and then we've got the two reactions, and we also want to include the 30-pound push. All right, so that's the free body diagram we could work with here. All right, so next here, why don't you calculate up what the normal and tangential accelerations would be? Okay, so why don't you do that? And once again, why don't you pause here, come up with what you think the normal and tangential accelerations would be, get those on there, and then we'll have a look. Okay, so why don't you pause the recording. All right, so hopefully you've paused the recording. You've got those normal and tangential accelerations done. Let's have a look here at what we think those are going to be. Now here they are. Now the tangential is 4.88 feet per second squared, and the normal is 11.94. They're in the direction shown. I've got the reactions there on the left, and then the 30-pound push. Now the normal acceleration is omega squared r, and so omega we need to define. So that's what's happening right here. See, we know what alpha is. It's 2.44 radians per second squared. We would multiply that by the time. Now, unfortunately, I set this problem up to have a time of 1 second, which makes omega equal alpha, which is a little bit unusual. That normally would not be the case, but on account of the fact I set the problem up with the time equal to 1 second, it turns out that omega is equal to alpha. Now, as I said, generally that would not be the case, but that's what we got for omega. So we plug that in and square it, multiply it by the 2 feet. Now, what the 2 feet is the distance from these hinges to the center of gravity, because the door's rotating around the hinges. So the radius would be from the hinges to the center of gravity. And then we multiply that out, and we get the normal acceleration, which is in from the center of gravity and towards the hinges. The tangential acceleration is just alpha times that 2-foot distance. It's 4.88. Okay. All right, now to finish this thing up, why don't you take one more step here and solve for the normal and tangential reactions there, Rn and Rt, in the normal and tangential directions. So again, why don't you pause the recording, give that your best run, and then we'll have a look at it. All right, so hopefully you've paused the recording, I should say, and there it is. So what we're going to do, we sum forces in the normal direction and set that equal to MAN. Now I'm going to call left positive on that because everything's going to the left, so I just went ahead and did that. So the normal reaction is equal to the mass, which we found earlier, 9.21 slugs, times the normal acceleration. So that's 110 pounds. That would be for both hinges together, that's the total load on both hinges. So it would be 55 pounds per hinge if you were designing the hinges. Now the tangential acceleration, I'm going to call in the y direction here positive, so that would be that way. Okay, so that's going up. I'm calling that direction positive, I guess I should say. So I've got some of Ft. So I got RT, the reaction, but I also want to include this 30 pounds over here. Those are the forces. They go on the left. And on the right, I'll put the mass, the 9.21 slugs, and the 4.88 feet per second squared. So when I work through that, I get the tangential reaction is 15 pounds. That's for both hinges. So the reaction per hinge would be 7.5 pounds. All right, so there you go. So that's finishing up that handout problem.